Hello and welcome to Columbia Physics Preceptor TV. Today we're going to talk a little bit about forces, but before we do that we have to talk a little bit about vectors. In physics, when you measure things, there are several different things you can measure, but some of them are mass, speed, distance, and temperature. We're not going to be dealing with all these today, but these are just some of the things you can measure in physics. Now, all these have one thing in common, and that is that you only need to specify one number. So, for example, you could have a mass of 1 kilogram, you could have a speed of 3 meters per second, or a distance can be 3 meters, or temperature can be 14 Kelvin. Now, like I said, these are only one number. Other quantities in physics, such as acceleration, position, force, and velocity, require not just one number, but they require several numbers. In particular, you need to quantify how large the quantity is and also in which direction. So you can have 1 meter per second squared for acceleration, but it's east. Or the position can be 4 meters to the right. The force can be 1 Newton up, and the velocity could be 3 meters per second left. You see that these also have the same magnitude that we were talking about over here, but they also have this direction attached to it. These things in the first column are called scalars, and these in the second column are called vectors. So we're going to talk a little bit about the properties of vectors and things you can do with them, analogously to what you can do with scalars. The first thing is we can find a way to represent these vectors, and that's just drawing them as arrows. Instead of drawing the writing velocities 3 meters per second to the left, we can equally well just draw an arrow to the left that has a length of 3 units. 2, 3. Or instead of drawing the force as 1 Newton up, we can actually draw an arrow up that has a length of 1 unit. And in doing so, we've transformed the problem of vectors into the language of arrows, and we are very comfortable with dealing with arrows. So the first thing we're going to talk about these arrows or these vectors is to add and subtract them. In order to add vectors, we can't just add the magnitude of them. So if, say, we have one displacement of 1 meter to the right and another one of 2 meters up, we can't just say that the total displacement is 3 meters. You can't just add the magnitudes like you do for scalars. Instead, you have to take into consideration the directions. So if we draw one arrow first, displacement of 1 meter. Let's say we're walking 1 meter to the right. Then we're walking 2 meters up. This vector should be twice as long as this one, and it should be directed upward. The net displacement, the total displacement, would be, well, we started here, we're ending here, so this will be the vector that quantifies the total displacement. It's not going to be to the right, and it's not going to be up. It's going to be at some angle instead, and the magnitude is certainly not going to be 3 meters, but in this case you can find them using Pythagorean theorem. So this is how you would add vectors graphically. It's called the parallelogram rule. So in general, if you have one vector in this direction, it's called A, and you have another vector, let's say in this direction, B, in order to add these two vectors, actually let's make B a little shorter here, so I can draw it on the board. If we want to add these two vectors, what we can do is we can move B, as long as we don't change the direction or the size of it, we're not really changing the vector. So we can move it as far as we want, and what we're going to do is we're going to move it right to the end of this first vector A. Moving B all the way over here. Now we can erase this first vector. Now we can see the analogy with displacements. Just like we had before, moving 1 meter to the right and 2 meters up, we now see that if we have one vector A and another vector B, the total vector A plus B would just be the vector that's drawn from one end of the first vector to the other end of the last vector. So this is a graphical way to add vectors. You can also do this algebraically. And it's the same thing. It's completely identical. It's just that you use numbers instead. So when I draw this vector A, instead of giving it a length, some length in some direction, I can equally well put in a coordinate system and give you the components of this vector. So let's say instead of A in this direction, you can split it up into two vectors and give me the length of each vector. So let's say this is 2, length of 2, and this is a length of, actually let's make this 4 and this 3. Then you can see that the total length of A is going to be 5, just using Pythagorean theorem. But instead of giving A as some arrow that you have to draw all the time, you can just say that A is equal to 3, 4. This uniquely determines the vector A. Now if I have some other vector, B, which is, let's say, 1, 2, it would be a third of the length here and half the length here, so about this. If I wanted to add these two vectors, instead of moving this all the way to the end, I can realize that when I do so, the x components, the first components, will add, as will the second components. So this means that A plus B is, first of all, 3 plus 1, so it's 4, and then 4 plus 2, 6. So that's the algebraic way of adding vectors instead of the geometric, instead of the parallelogram rule. But they're completely equivalent. Okay, so this is all the stuff I'm going to talk about vectors. Let's talk a little bit about the physics. In particular, let's talk about forces. Like I mentioned on the list before, forces is a vector quantity, so we need vectors to describe them. In particular, there are many different types of forces, but the ones we're going to be dealing with today are gravitational forces and spring forces. When I hold something in the air, it wants to fall down, and the force at which gravity pulls it down is equal to its mass times the gravitational acceleration, g. G is equal to 9.8 meters per second squared. For the spring situation here with spring forces, if I have some spring and I stretch it, it's going to try to pull back. Or if I compress it, it's going to try to push me out. So let's say I have some spring which has a rest length of this distance here, and I pull it out a distance s. Then the amount of force it's going to pull back at me with is equal to, F spring is equal to some constant k that depends on the material of the spring, how tightly wound it is, all these properties of the spring. It's called the spring constant times this distance s. That's the magnitude of this force. It's going to pull me back if I pull it out, and it's going to push me out if I push it in. So this is something that's specific to each spring. So let's say I had a spring with spring constant 2 newtons per centimeter. And let's say I stretched it 3 centimeters. Well, then the force would be k times s, so in this case it would be 6 newtons. All right. The next thing I'm going to talk about is equilibrium. If something's in equilibrium, that means that it's not accelerating. So suppose you have 2 people, or let's say 3 people, pulling on some object here. You have someone pulling in this direction, maybe someone's pulling in that direction, someone's pulling in this direction. Now they might not be pulling equally hard, but let's say this first one pulls with a force F1, and the second one with F2, and the third one with some force F3. Newton's first law and second law say that if this thing does not move, or if it's not accelerating, then these forces all have to exactly cancel out. And by what we mean about that is, of course, that the vector sum of these 3 forces have to add up to 0. So if we actually drew them out, F1 here, and maybe F2 going a little bit to the left, and F3 going down, they all have to add up to 0. They all have to come back to the beginning. In this case, the net force is equal to 0. So suppose you know 2 of these forces and the fact that this doesn't move, then you know basically what F3 is. There's another aspect to equilibrium which has to do with rotation. Suppose this ring here wasn't moving, but it was still rotating, speeding up faster and faster and faster, then it still wouldn't be at equilibrium. So equilibrium also includes the fact that the rotational speed of this thing can't change. In order to deal with that, we need something called torque. Torque is kind of similar to force. It includes the force, but it's slightly different. I'm not going to go into detail exactly what torque is, You'll hear about that later on in the semester. Instead, let me just give you a quick definition, or a quick example rather. Suppose we had some rod that's balancing on a tip here. Suppose we hang some mass of mass m1 here and another one of mass m2. Also suppose that this thing is actually pivoting on a point that's a little closer to m1. Let's say this distance is d, and this distance here is 2d. Instinctively, you know that if this balances, then since this distance is much shorter than this must be much heavier than that. And that's exactly true. And torque is just a way to quantify this. It tells you that the force times the distance on this side has to equal the force times the distance on the other side. So in this case, since the force here is purely gravitational, if you remember I just wrote down the gravitational force is equal to mg, we have the force times the distance on this side is m1g times the distance. On this side, the force is m2g times the distance, but this time the distance is 2d. In order for this not to tilt back and forth, or for it to remain in equilibrium, these two have to equal each other. And we see that the g's and d's cancel out on both sides, and that in fact m1, the mass on this side, in fact is exactly twice as heavy as the mass on the other side, just like we had expected. So this is pretty much the experiment you're going to do today. Let's start with the first part of the experiment. Here you're going to have a table with 3 pulleys on it. And they're all going to have, there's going to be one big string, or 3 strings that are tied together in a knot. And they're going to be running over these pulleys. And each of them are going to have a mass attached to them to pull them down. You're going to know 2 of the masses. Let's say you know this one and this one. But you're not going to know the third mass. Then, by requiring that this thing stays in equilibrium, you can use, just like we had with the 3 people pulling on that object before, you can say that the force due to these 3 has to add up to 0. And the exact way you're going to do that, you're going to have a piece of paper under these strings, and you're going to trace out exactly what these strings look like on the piece of paper. And since you know what these masses are, you can exactly scale how long each vector should be. So you'll get something like a vector here. Let's say this is 100 grams, and it's 150 grams. Then maybe you can make this 10 centimeters long, and maybe the other one can be 15 centimeters long. And then you don't know how long the third vector is going to be, but you know it's going to be along this line, along the string. And then by adding these geometrically, you can figure out exactly the length of the third vector for these to add up to 0, and hence you can figure out what the unknown weight is. A small thing that you should think about when you draw these is, depending on which angle you're looking at from the top, you might get different lines. So you're going to want to use a mirror below it to make sure that when you're looking straight from above, the mirror image should be exactly behind the string, so that you don't, so that there's no ambiguity in which line you should be drawing. So that's parallax. You want to get rid of the parallax. The second part of the experiment is in regards to springs, and it's pretty straightforward. You have a spring, and you're going to pull on the spring with a given force. You have these devices that you pull on with this with, and you can measure exactly what the force you're pulling with is. And then, by knowing the force, and you can measure the distance that this thing extends, you can graph the force versus the distance. And since the force should be equal to the spring constant times the distance, you should get some straight line. And the third part of the experiment is in regards to this torque. This time you have, just like we had before, a little rod that balances in the middle, and on this side you have one hook, and on the other side you have many hooks, given distances away from this point. You're going to hang some given mass on here, and you're going to use the same device to measure the force required to keep this at equilibrium at the various points over here. So then you're going to have some force related to this hook, and some other force here, and some third and fourth forces over here. Then you're going to be able to graph the force versus 1 over the distance. So this is a distance. Graph force versus 1 over the distance and see what you get here. You should get, again, a straight line. All right, so that's pretty much the experiment. Let's see. Yeah, that's pretty much it. Have a good one.